Welcome everyone to the ASEAN Smart Mobility and Modeling webinar. Today we'd like to introduce you to the practice and process of transport modeling. If the topic of transport modeling is new to you, that is not a problem, that's even a good thing, because today we'll start from the very basics and work our way forward. And this session today is brought to you by the ASEAN GIZ Summer Project, by PTV Asia Pacific, the PTV Group subsidiary here in Asia, who is the industry leading software solution developer in the space of modeling. And we also have App Vantage with us today. Just a quick note about me. I will be delivering the first and main part of the session today. For those of you who I have not yet met, my name is Conrad Richardson. I currently work on the GIZ project called Summer Sustainable Mobility in Metropolitan Regions in ASEAN, and I work as one of the technical advisors. I am based in Cambodia, but work across the ASEAN region, and I began my career with PTV Group, the company I previously introduced, and through them I got an introduction and insight into transport modeling tools, which I have since used in a variety of different projects in different geographies, and as of lately in the ASEAN region. Brief note on the Summer project. Summer is an ASEAN GIZ sustainable mobility governance project, and through this project we support metropolitan regions in ASEAN develop sustainable mobility concepts and strategies. And we do this in cooperation with the ASEAN Secretariat in Jakarta through the Land Transport Working Group. And as part of our project, we do a mix of capacity building through events and networks like these, as well as project visioning and technical assistance. And for instance, we're currently working on an ITS and CCTV analytics project in Cambodia, a cross-border cable car project in Thailand and Laos, and a quality bus corridor in Can Tho in Vietnam. For more information on our project and our different activities, do consider checking us out at www.summer.asia, or also find us on LinkedIn and Facebook. And one final note, we are currently setting up new thematic networks, 3 in total. Today, this event pertains to number 2, the Smart Mobility Governance and Management Thematic Network. And next year, we'll be launching more comprehensive courses, curriculums around these different topics. And in the second one, we will cover the fundamentals of intelligent transport systems, ITS, and data, touching on technical requirements, but also governance. And in this thematic network, we will also look at modeling. So we will include this particular session, but we'll also go in much more depth and include some very hands-on training. And I hope I can also travel to some metropolitan regions and co-develop projects with you that include a modeling component. So again, stay tuned for these, and if you want to stay up to date, do follow us on social media and check our website every now and then. So let's get into the modeling webinar. So today, we will introduce you to modeling. We will cover theory and look at some practice, and we'll do it in these 3 different steps. What is modeling, why it's important, modeling use cases and case studies, and data requirements. And then Paul and Sharan can also give you some insights into the user interface and other PTV tools. And let's start with the very basics, covering some key definitions. So what even is a model? You can give it some thought, any ideas? So essentially a model is a representation of an object or system. Essentially it's a simplified version of something, and we come across models all the time. There's many different kinds. For example, we have physical models that could, for example, be an architectural mock-up, or we have schematic models. Here we have a public transport map, which is essentially a representation of the real world public transport system simplified into a map. We have verbal models, like a business model, which is a representation of a business written up in a verbal document. And then we also have mathematical models, which is what we'll be looking at today. And I don't want the word mathematical to scare any of you. We have excellent tools that mean it is possible to develop these very complex models without using any complex mathematics. But mathematical models make up transport models. So what is a transport model? Well, one definition is it's a practice and process that uses software tools to virtually test, appraise, and visualize complex concepts. So that's very useful. The world is becoming increasingly complex. If we have tools that help us find comfort in this complexity, that is a good thing. So why do we model transport? Well, to find comfort in complexity, but the more academic explanation would be to balance the supply and demand of transport systems in the present, but more importantly in the future. And here I have a hypothetical example of Germany in 2020 versus Germany in 2030, assuming there's a 10% increase in road transport. And using a model, you can visualize and test and appraise how the network would perform with the same supply of infrastructure with a 10% increase in demand. And you can see that there's a significant increase in congestion, which would have a macroeconomic cost and slow down the economy. And you can get a general idea of this, at least from a transport perspective, using a modeling solution. But also using this solution, you can also design, test, appraise, and evaluate different concepts and solutions to absorb the growth in demand. For example, you can increase the supply of road infrastructure by adding new roads or new lanes, or preferably by increasing the amount of public and bus and rail-based transport. And all of this can be done in modeling solution. And I think it's worthwhile saying modeling software is not cheap, maybe compared to GIS tools, or you might be familiar with the price of Photoshop. These are far more technical tools, and they do sound expensive, but they are significantly less expensive than making mistakes. Road building, infrastructure construction is very costly, and mistakes can cost. So it is really worthwhile making use of these tools so you can really test, define, and refine your concepts all in this virtual environment. But modeling isn't perfect. There are many limitations. The real world is very complex, especially in the ASEAN region. Mathematical models and algorithms can only go so far. They can only factor so many variables, but the real world is really so complex. And this is an aerial image from Ho Chi Minh City. And if you've been to Ho Chi Minh, there's a lot going on. And creating a model that factors all that is challenging, but it is possible. And these tools are continuously improving and can be continuously or increasingly customized to reflect different realities. But at the end of the day, these models remain only approximations of reality, even though they're always improving as we get better at collecting data and building and increasing the precision of our models. Despite these limitations, we have to consider the risk of not modeling. Really, models are not perfect, but they're the best thing we have available to us today to make these big, complex decisions. That's a little bit of theory. If you want to continue learning, this is a textbook I can only recommend. It's really the Transport Modeling Bible. And moving on, now we can look at the different scales of modeling. So there's different kinds of models. It's not just one kind of transport model. We have a spectrum, and the spectrum depends on the scale or level of detail. On one end, we have macroscopic models, so very large scale models used for transport planning purposes. So this could be for the entire ASEAN region, or an entire country, the country of Vietnam, or a metropolitan region, or an entire city. And these models are usually link-based. All the information is stored in links. You don't see agents, vehicles, anything like that moving around. It looks a lot more like a GIS interface. Then if we move down the scale, we have a mesoscopic scale. I won't go into detail on that today. And on the other end, we have the microscopic scale, which is used for transport engineering purposes. These are also models, but they're commonly referred to as simulation, so simulation tools. And in these models, we model individual agents. And I'll explain that in a little more detail in a few slides. And PTV, who is here with us today, they have different solutions for all the different scales. And there's many companies out there, but PTV is the only one that has the whole suite of softwares across the different levels of detail. And the solutions are more or less integrated. So Visum models can be imported in Vissim, and Vissim and Viswalk can coexist in the same interface. So it's nice, and you can have a good workflow between all these different solutions. And I'll show you another example of that later on as well. So just to make it crystal clear, Visum macroscopic modeling for planning purposes is link-based, or also node and zone-based. So the link is essentially a road, a piece of road, a line in the software. A node is a grouping of lines, and a zone is a larger area, a larger grouping. So you'll hear these words throughout the presentation. And then on the other end of the spectrum, we have PTV Vissim for transport engineering purposes. That is agent-based. And agents are autonomous agents that act on simple decision-making rules. So you have literally individual people and vehicles, and they move around and they adapt to their surroundings. So it's much more granular. Both macroscopic and microscopic modeling have their own workflows, but they can be simplified and can be very similar. And the typical transport modeling workflow looks a little bit like this. So here we have a hypothetical project location, and you are the planner, the designer, or the engineer, and you are asked to improve this particular location. It's a roundabout that looks a bit like an island. It's nice, but I'm sure it's not very pleasant accessing this piece of public space. And then once you're there, you can hear traffic the whole time. So maybe there's ways it could be improved. So say that is your job. The first step for you is to develop a vision of how the space could be improved. And your vision could involve improving pedestrian mobility, beautifying the space, giving public transport priority, and improving the ambient air quality in this particular location. And how can we do that? Well, the next step is to build the base model. And a base model is essentially a model that reflects the existing situation. And for this, we need to collect data, up-to-date data from this particular place. And this data will typically include traffic counts, so the number of vehicles moving through this road network, turning counts, so how many vehicles are turning where. You will also need road network information, so information on the road geometries, the number of lanes. The traffic light information is also useful, and also information on vehicle compositions. So which kind of vehicles and how many are driving through the network. So how many heavy goods vehicles, trucks, motorbikes, cyclists, cars, etc. And then useful but not necessary is also 3D objects, which you can use to create a nice visualization of your project or vision, or your base model in this case. Next, we develop the model using the data we collected. And lastly, we calibrate our model, which is the process of making sure that our base model developed in Vissim reflects closely what happens in reality. And you can do that by comparing your model with, say, video footage and tweaking it and adapting behaviors so that it closely reflects the reality. So once you have your base model, the next step is to develop scenarios. So let's keep it simple. We'll look at two different scenarios, A and B. And in this instance, scenario A, this is the idea the planner, engineer, designer has come up with, and it involves creating this pedestrian overpass with these smooth, low-grade access ramps, and there's also space for real estate development. And there's significantly less space allocated to vehicles, but it's not particularly pleasant. So I don't know if it's the best in terms of beautification. So let's consider another scenario, scenario B. Here in scenario B, we have an elevated park that would really remove people from the roadway. And I would consider this to be a much nicer looking option, probably much more costly. And once you've developed your two scenarios, the next step is to test and evaluate these scenarios. And in Vissim, you can test your network performance, the travel time it takes to move through the network, the delays, the queues, and all of this you can compare. And then the very final step is to validate and select your preferred scenario. So this is just one example. It's not highly technical, and your final scenario selection could look something like this. So this is all built in Vissim. However, the modeler has also built some 3D objects in Google SketchUp. So the buildings in the background, which don't add anything to the scientific validity of the model, but it just looks nice and creates a nice output which you can use to communicate the project to the public or to the mayor. And this is all built using real data that was collected in the base model. So that was the workflow. Now I think we can look at a couple more use cases and case studies for Visum, Vissim, and Viswalk. And we begin by looking at microscopic modeling use cases in PTV Visum. And PTV Visum is a software solution that can be used for traffic analysis, demand forecasting, planning public transport services, and GIS-based data management. So if you're not familiar with these, or it doesn't make sense yet, I will give examples for some of these. And so here we have our Visum network. It's a network for a medium-sized city, and this is what you would probably see in your screen, or the section of your screen in your network editor. And here in brownish purple, we have the highway. In yellow, we have secondary roads. And when you click on an individual link, you can see information from this link. So here you have lots of different attributes: the link name, that could be the street name or just an ID number, the length, the number of lanes, the capacity, the speed that one can drive on. So all of this information gets stored in the model. And for example, you can also view all the public transport stops. Here the triangles are the bus stops. So it really serves as a space for storing geo information, but it can do much more. You can also run assignments. And when you run an assignment using origin destination data, you can see the volume of transport on the different links. So here in orange, we have private transport. In blue, we have public transport, and the thickness of the bar represents the volume. So if we zoom in, you can see here private transport. We have 5,500 vehicles driving on this link, and 1,002 public transport riders, not vehicles, moving across this link. And you can do a number of different visualizations. You can see the extent to which they're moving at free flow speeds, etc. And all of this volume information is based off an origin destination matrix. Well, actually, in this case, of two origin destination matrices, one for public transport and one for private transport. And this is essentially what the matrix looks like. So here, just as an example, from Park to Innenstadt, so to the city center 1, there are 14 vehicles moving from this node to that node. And I'll explain in more depth later on where and how this data can be collected. With this OD matrix methodology, the model knows the origin and the destination of a person, a data point, but it doesn't necessarily know how they get there, or the model will calculate that. And it doesn't know which route they will take, but generally a rider will take the shortest route available, which is a factor of distance and time. Distance in a congested urban area becomes less relevant, so it's a factor of time. And one of the many applications of Visum is to plan upgrades to the transport network. So here in this example, we can use Visum to introduce a new bridge and assess the impact this bridge would have on the overall network performance. And this is very quickly done. You can draw new links and connectors and create a new bridge. And then you rerun an assignment, and in a matter of seconds, you will know the demand on the new bridge, but you can also see how the demand has shifted from other locations in the network. And so you can appraise the impact this bridge will have on overall network performance and see whether or not it is worthwhile, or make decisions on how many lanes this bridge should have, and so on and so forth. And we can do all of this without doing any complex calculations. The software does this for us. So Visum can be used for a wide variety of applications. It can be used for road infrastructure planning, like we just saw, by introducing a bridge. It could have been a new road, a ring road, or a tunnel, or adding a certain number of lanes in different locations. Or it could be used for doing demand forecasting. So this could be our base model, and we have certain assumptions about what's going to happen into the future, and we can understand how the network performs factoring these forecasts, and we can look at different interventions, again going back to new road infrastructure planning, to absorb this capacity. And Visum can also be used for public transport planning, so creating new public transport routes, or changing a public transport schedules, or to understand fleet requirements of your transport system in the present, but also in the future. So that's everything for Visum today. Visum is a very powerful tool, and we could do an entire series on Visum. So maybe in the future. For now, we'll leave it at that, and we'll focus on microscopic modeling. So back to microscopic modeling, we have the tools called Vissim and Viswalk. These are traffic engineering simulation tools. Vissim for vehicles, Viswalk for pedestrians, and these are fully integrated. And you can use these tools for a wide variety of applications, for simulating private transport, public transport, active mobility, parking, traffic signals, simulating vehicle emissions, and in this tool we can also do some nice 3D visualizations. And Vissim is based off the car following algorithm. It's known as the Wiedemann car following model. And you don't really need to know this, but it's worthwhile having a basic understanding of how vehicles move. Basically, vehicles don't drive at a constant speed from each other's bumpers. They get closer and they move away, and that depends on behavior. Same goes for turning behavior. And this also differs from country to country. In some countries, people drive more aggressively than others, and this algorithm can essentially be tweaked and adapted to the local driving condition. Then looking at PTV Viswalk, this is a pedestrian simulation tool, and they have their own algorithm. Humans move very differently to vehicles, so the car following model is used for all vehicles, including bicycles, that essentially can only move forward and backwards and then turn. Whereas people, we can move in all directions and humans obviously behave very differently to vehicles. And so in Viswalk, the movement of people is based off the social force model, which is a different kind of algorithm. And this can also be customized. So people prefer different levels of personal space in different parts of the world. In Southeast Asia, people seem to be less discontent having people close by compared to, say, a Nordic country. In Norway or Sweden, people like their personal space much more. If someone gets within 2 meters of you, you start to panic. Whereas in Southeast Asia, that's not so much the case. And all of that can be customized in the model. And obviously this differs depending on the setting that you're in. In tight spaces, people move and adapt differently. So that can all be emulated in Viswalk. And in Viswalk, you can start to assess capacity and the level of service of certain infrastructures. Level of service can refer to the comfort level a person might have when they're moving through a certain space. And here we can see it goes from A to F. F is very unpleasant, especially if you're trying to move and trying to get somewhere. This will not be free flowing. People will be tripping over each other. So level of service F is not good. C is acceptable. It's slightly restricted, but it's comfortable. So when planning an infrastructure, it's good to aim somewhere between B and D. And here we have a nice example of a train station and a big multimodal interchange. You can see as the pedestrians alight or disembark from the vehicles, you can see the level of service. And here, for example, there's a level of service F. There's a bottleneck forming before the stairs. So if this is a plan and this has not yet been built, maybe the architects could consider widening the staircase so there's more throughput. And here as well, there's a very poor level of service. So maybe there's some spatial modification or intervention that could be brought in to improve the flow of people. But then overall, in the rest of this space, there seems to be a decent level of service. Pedestrians are leaving the station and interchanging onto buses, and it's quite neat. You have a good mix of public transport, pedestrians, and vehicle-based transport. So this particular example uses Vissim and Viswalk. So different use cases and applications for Vissim and Viswalk, or specifically Viswalk. One could be to do capacity analysis. So if you're designing an airport, you might want to know at a certain time of day, maybe at peak hour, how many passport control checks do you need? How many security bag checks do you need open? And you could use a tool like this to appraise that. Or you can use it for multimodal engineering to model the interaction of people from a public transport system, moving through a road-based network and entering a car park. Or you could use these tools to plan an event, to understand the movement of people to and from a stadium, or to evacuate a stadium, and to determine if you have enough exits for people to exit in a timely fashion to avoid any major incidents. So Vissim and Viswalk are very versatile. And I'd like to look at some more real world case studies. Does anyone know where this location is? This is an old aerial photograph of Trafalgar Square. It's over 100 years old. This is a critical location in London. It's arguably the city center of London. The city sort of radiates along these different axes. And here you can see it essentially forms a big roundabout. Trafalgar Square was a big roundabout over 100 years ago. And you have 3 lanes of traffic here, 4 lanes here. It's a space really designed for the movement of vehicles. And London at the time was a much smaller city, probably 10 times smaller, had significantly fewer vehicles, but they had all this space allocated to the movement of vehicles. Now, if we look at it today, the space has changed considerably. If you have a good look, you'll notice that significantly less space is being allocated to private or to vehicles in general. and much more space is now allocated to pedestrians. So this street has been closed off. It no longer serves as a roundabout, Trafalgar Square. And instead, they moved from this big 3 to 4 lane highway or roundabout to a small 2 to 3 lane roundabout you see here in the foreground. So how is this possible? How can they do this? London has only grown in population, and the number of vehicles on the streets has only increased, and this location has only become more popular. I think you can even see the buildings are taller than they were before, and if you present this concept, it will never pass, because you cannot have this location in London congesting. It's simply too important. So how do they justify closing off this space? And just as a side note, this was done using a grant from UNESCO. They consider this to be a very important World Heritage Site and symbolic space in the world. So they provided Transport for London and the City of London with money to close off this space. And the way they went about designing this new space was using Vissim. And this is much more than a design-based project. It's a project that relates more to traffic signal management. And what they did was they developed a queue relocation strategy. So all around Trafalgar Square, you have these different arms approaching and different junctions lead here. And this particular location cannot congest. Congestion here would create many problems for the city. So what they did was they built a Vissim model. They tested this new geometry. It didn't work. It overly congested, and there was a knock-on effect in different parts of the city. So they reprogrammed the traffic signals. And basically, all the traffic signals in and around this roundabout, they can detect the threshold. So how many vehicles are waiting to move through this space. And when these traffic signals reach, say, a 60% threshold, they send a message to the traffic signal upstream saying, hold traffic back until I can get closer to free flowing speed. And by using the network of traffic signals to hold traffic back at less critical locations, they can ensure that the flow of vehicles here is always smooth and constant. And all of this was tested and proven in Vissim before it was implemented in the real world. And so today we have a nice public space. We have free-flowing traffic, more or less, in the foreground and around the roundabout. And then the traffic signals are all optimized in these locations. And of course, this coupled with big investments in public transport has made it possible to keep growing the city. But modeling has played a very important role in increasing the movement of people while working with a very limited amount of road space. Here, I think it's important to show you more local examples. This is just a model showing you non-lane-based traffic behavior. So in many cities in ASEAN, vehicles do not abide lanes as they do in some European cities. So in Vissim, by the tick of a button or flick of a box, you can switch off lane abiding behavior, and vehicles now, whenever they see a safe enough gap, they will move into it. So this much more closely resembles what happens in Phnom Penh in Cambodia, where I'm currently sitting, and the model has this type of functionality. Now, I just wanted to also show you how you can do some high-end visualization in Vissim. So this is another project where the public realm was improved, again using a roundabout and giving pedestrians more priority at this particular location. And the tool was used to see whether or not this was viable and made sense, and also to get a sense of how it would look. So this is all made in Vissim, but then it's rendered in 3ds Max, and you can get these very cinematic outputs. And now I'd like to show you very briefly how these different solutions can be used together. So Visum, Vissim, and Viswalk, say, for one project. And let's take bus rapid transit as an example, a BRT system. So we want to design a BRT system in our city. We can take Visum, bring in all the GIS data that we have on the existing road network, land use information, economic information, and with that we can do some demand analysis, understand the different socioeconomic groups and where they live in the city, and decide where we can put or identify the optimal location for putting a corridor, and then planning this corridor. And then once we know where our corridor is, we can do some preliminary rolling stock planning. So deciding what kind of vehicles we would like and running an assignment to see how this performs, what the volume is, and how we can cater to the anticipated ridership. And then continuing with Visum, we can use Visum to then develop our timetables, our schedules. We can run through several iterations until we find a good timetable that really matches the supply of buses with the demand for trips for different hours in the day. And you can do all these visualizations in Visum. So this, for example, at 6:30 a.m. from Stadium to Central Station, there's not much demand. It does get busier from Central Station to Market Square later in the day, but 6:45, you see here, there's a lot of demand. So maybe this could be an indication, maybe we should include an additional bus around this time period. And all of this can be done nicely in Visum. And once you know the demand, the supply, you can also design your transit fares accordingly and get a lot of information to help you finance this kind of project. Because you can use Visum to determine your return on investment, your payback periods. So it's a very powerful tool in that sense. And once you're done with your planning, you move over to the engineering stage. Here, it's a Vissim model from Abu Dhabi, where they wanted to understand the impact of introducing a BRT corridor by removing a lane of traffic. So obviously there's buildings on either side, and they were not able to knock down buildings, but they wanted to increase the throughput of people. And this is measured by PPHPD, which stands for per person per hour per direction. So with 3 lanes, this corridor can move 7,000 people per hour per direction. By introducing a high capacity bus, you can increase the number of people moving through this space by 3,000. So 10,000 people per hour per direction. And the tool like Vissim is very powerful in showing that you can remove road space if you introduce a higher capacity alternative like a BRT system here. So I quite like this example. And so once you've done your corridor engineering, you might want to give a little more detailed attention to your intersections. And with bus projects, you can give priority to the buses. So when they approach the intersection, they can communicate to the traffic signal and get a green wave. But the levels of priority can differ, and you can understand the impact of that. So here, for example, we have low priority, so the bus barely doesn't get a green light when he arrives at the traffic signal, versus high priority. So the bus arrives, there's very little delay, light goes green. And that can make public transport more convenient, more competitive, reduces travel time, which is makes public transport relatively more attractive to alternatives. And here you can do all these evaluations in Vissim and watch how the different scenarios perform against each other. So again, high priority, very little delays. So that's probably a nice thing to look into when designing this type of bus corridor. Okay, this is just an example I found on YouTube of the Line 1 BRT corridor from Ho Chi Minh City. It's on YouTube, and it's the whole pilot corridor in one model, which I think is quite nice and summarizes a lot of the things we've spoken about. You have the BRT, the stations, parking, you have different lanes for motorbikes and vehicles, you have non-lane abiding behavior, and you have lots of pedestrians moving to and from the buses. So this is a really impressive model, and I think if you go back to the beginning, you can see the sheer size of it. So this is all along Vovanket Boulevard down south, and I think it gets close to Boy Bentan. Yeah, if I remember correctly. So just another example. We can get more granular. You can also use Vissim plus Viswalk now to design your station platforms. You may want to see how vehicles enter the stations, how long your stations need to be, how to bring in passing lanes if that's necessary, how people access the stations, how they board and alight the buses. All of that can be tested in Vissim and Viswalk. So this is an example from the Transmilenio in Bogota in Colombia. And then very lastly, using Viswalk, if you wanted to get creative, you could also test the impacts of different bus designs. So you could compare what would happen if my BRT system operated with a bus that only has 2 doors, or 80 seats versus 100 seats. You could compare that. And obviously, if you have more doors, people can board and alight quicker, and that could make the service operate slightly faster or more smoother and reduce any potential delays. And you could then appraise the economic cost of having an additional door and whether or not it makes sense over a long span of time. Okay, so last section, it's worthwhile talking about the data required to build these models. And again, we'll do it for Visum, macroscopic modeling, and then microscopic modeling. So for Visum, we previously spoke about origin destination data, OD data, and there's traditional methods that have been used for decades at this stage. And to do an OD survey, you manually go out and you sample a number of people, and you go around your different city and you ask people questions. And what you want to do from your OD survey is understand who uses the transit system. So you want to get demographic data. You want to understand why they use it. So are they choice riders versus captive riders? And then information on when, where, how, and for what they use the transport system. And here's an example of an OD survey form that you might have, and you go out and you ask these people these different informations in different parts of the city, and you can build up a picture of how people move in a city. It's very labor intensive, but it's the method that we have used for a long time. And it's also, well, here I have a slide touching on the limitations of origin destination data. So, or collecting it in this traditional way. It's costly, it's labor intensive, you have limitations to your sample size, the quality of your answers can vary, not everyone loves answering questions, and then there's also temporal limitations. It can take several months, years to collect this data, and then it takes time to model. And by the time you build your model, maybe the data you collected does no longer closely reflect reality. That can be the case in cities like in Phnom Penh, where I'm currently sitting. The city transforms on a month-by-month basis. So if it takes too long to collect the data will be less valid or no longer valid in the future, and that results in an oversimplification of reality. So household surveys are somewhat outdated, but they still have a lot of value. There are, however, new methods to collect origin destination data. And if you wanted to create a public transport model, you could source data from public transport smart cards, if that's something you have in your city. You can get information on people boarding and or alighting the bus, so you know where people are going to and from, more or less, or if they're interchanging from, say, an LRT or MRT to a bus. You could get that data, which can be useful, but not everywhere has that. Or you can use GPS-based apps. A lot of apps collect information on people and their movements. If you could access this kind of data, if you could buy it, for example, from Grab, I don't think Grab sell this data, but there are a lot of data aggregators who package and sell data of the movement of people. It's often anonymized, and using that data, you can also build up a picture of origins and destinations of people in a city. Another method is using cellular data. So we all carry smartphones, and I'll show you exactly how that works afterwards. But each of these methods has different benefits. Smart card data gives you real-time information, trip history and frequency, transfer data, while location service apps can give you very precise location information. You can get real-time door-to-door information, so from someone's house to someone's office, which you cannot get with smart card data. You only know when they boarded the public transport vehicle and got off. And you can get some information on the passenger and maybe pricing information, how much they're willing to pay for transport. And then mobile phone data, that's also useful in its own ways. You can get real-time door-to-door origin destination. Mobile phone data is constantly being generated, it's widely available, and you can get information on a 24/7 basis. Assuming it's accessible in your location. Not every country or company sells their data. And there are, of course, limitations for all the different kinds of data. So with smart card data, you don't know first or last mile. With location services apps, there can be data interruptions, or there's a bias towards younger people. And with mobile phone data, the data is, there's modal limitations, I'll explain that later, and the data is anonymous, so it limits the socioeconomic analysis you can perform. But just one slide on cellular data. It works basically on cells, and you can see people as they move through different cells, and cells are normally in this polygon shape. And this information can be packaged by the telecommunications companies and sold on to cities, planners, consulting firms. But of course, there's many limitations. Short trips inside cells cannot be captured. The type of trip activity can't be picked up. It's just not detailed enough. There are privacy and bias issues towards young people. And it's really hard to extract the mode of transport someone is using. There are ways you could build an algorithm that can make assumptions and identify the movement of cell signals when it's close to, say, a metro line. You could make an assumption that these people are in the metro and there's a high density of people moving at a constant speed, and you can make assumptions there. But on a smaller bus, it becomes very complicated. So what is the best method? The best method is, I would say, a fusion of the traditional methods with the new methods. So surveys plus, say, mobile phone data, and you get a wide range of different kinds of data. Say in the Southeast Asian context, you use mobile phone data, existing land use data from OpenStreetMaps, for example, the public transport network. So if you have existing GTFS data, that's great. Or you work with someone like Where's My Transport, then you get some census data and survey data. And you bring all of this together and you clean it, you select the relevant samples, you expand on the samples, and you fuse all the different data sources, and you use different algorithms to detect different mode types if you're working with cellular data and the potential activities people are doing. So there's a big process of data cleaning, fusion, processing. And then in your output is you get a fairly realistic and robust travel demand model. And again, it's only an approximation of reality, but oftentimes this is sufficient for the work you're doing. There is another method if your city has existing ANPR cameras, and you can detect the movement of vehicles through the network based off their number plate information. That's also another option. And lastly, let's look at microscopic traditional data collection methods. So now looking at Vissim for traffic engineering, what kind of data we need? It's quite straightforward. We need vehicle compositions, and counts. So how many people drove straight, how many people turned, how many people turned left, right, at each and every intersection, and also a note on what vehicle they were driving, and information on the behavior, so how fast they were driving. And this is the traditional method. You used to go out with a form and you would do counts and just check off how many cars you saw, how many trucks you saw, going straight, turning left, turning right, etc. Nowadays, there are more innovative methods. So in Cambodia, we're currently working on a CCTV analytics project. And essentially, we trained an artificial intelligence to detect the different kinds of vehicles in Phnom Penh. This is an early example. So here we can detect tuk-tuks. And every time a tuk-tuk drives through, we know for the period of time how many tuk-tuks drove through. But now it's much more sophisticated. We can do that for every vehicle type. And this data we could then very quickly import into Vissim. Music off. You could use a drone, fly it over an intersection for a period of time, say up to an hour, and count the same information from above. And there are tools and systems in place that can give you useful raw data for easy import into Vissim. So here's a corresponding Vissim network, and that is much, much faster than going out and counting vehicles yourself. So it's good you can leverage these new automated solutions, camera-based solutions, whether they're on a drone or set up on a gantry, or using existing police cameras that are existing on site. If you can get access to the cameras or even just a sample of footage and plug in your analytics solution to count, categorize, get vehicle speeds, that is one more, a faster and more modern way to collect this kind of data. Okay, that's everything from me. Encourage you to reach out if you have any additional questions, and if you'd like to take it a step further and download the software, there are free demos online. There's a lot of resources online on YouTube, and in the future I would like to work with you, help build your knowledge on transport modeling. So feel free to get in touch and follow us on the Summer website, and yeah, I hope that was interesting.